And hopefully you can hear me now. Welcome to what is day 5 of this software session C and C++ tutorial. My name's Andy, and we've had quite the journey here. In the description, I've listed out all the other videos. You can go check them out. But we've sort of started off with the basics, gave a nice overview of that, moved into some pointers and what that's all about, moved into the differences between C and C++, moved into networking yesterday, and you got to see some debugging and some intricacies there on networking. And then finally, we're going to end this with parallel computing. And this is a topic near and dear to my heart. I spent a long time doing research in parallel computing, so we're going to go down that path. Before we get too deep into this, though, in case you are just catching this particular one, and maybe not the others, I do want to share a few things with you on the screen here, and we'll go from there. As always, if you have comments or requests or questions, feel free to let me know in the chat or after the video posts in the comments. I'm going to be attentive to those as best I can. And of course, if you need to reach me, you can reach me on my blog. I'll switch over to that. Here we go. So the blog here, Software Sessions Day 5. You can leave comments, you can like it, you can do all that sort of stuff here. And then also all the project materials are posted up here on GitHub. I haven't posted anything in advance of today's because part of the configuration of the project is going to be a subject for today's class, so we'll go with that. The other thing I did want to point out here, just as I start looking through things, is this idea of a cheat sheet. So I posted it up on the blog. You can find it right here. It's a OpenMP cheat sheet with some lovely quick syntax guides. So we'll go through a number of these today, and that will make life a little bit easier for you. So if you are interested in seeing this cheat sheet, I'll try and throw it also in the description down below, but at least in the short term here, the link is off the blog, and you can check that out. And this will give you a little bit of explanation over everything that we're going to touch today. We're not going to touch everything that you see here. We'll just touch probably most of it, but yeah, we'll go from there. So let's move on. So I'm going to get Visual Studio here up and running. And that should mean we can create a new project. So here we go. Creating our new project. It's going to be a console app. We're going to call this, we'll call it Parallel Computing. It's a great original name. And we'll click OK. Cool, cool. Okay, this gives us that same sort of hello world file, and I'm just going to clean this up. We're going to need a few includes to start. So we're going to include omp.h for OpenMP, and we're going to include our standard I/O because we'll want to print stuff out. So and I'll clear out my main function here. As you know, I have my vendetta against precompiled headers. You might like them, I personally don't, so I'm just going to clean those up too. And now we need to do some configuration here on our project. This is highly Visual Studio specific on this configuration. It's actually a lot easier to do if you want to do it on Linux, and if people want to go into OpenMP much more, or they want to do it in Linux or something like that. Feel free to give me a shout or leave a comment because doing it in those environments is a little different, and there's a lot to discover in OpenMP. You can target accelerators, you can do lots of stuff like that. So this is just like a big can of worms, and I'm just going to give you the absolute basics in this, and we'll go from there. So we have a couple things we need to turn on now. I turned off my precompiled headers, but we're going to want to turn on our multiprocessor compilation. Yep. and then I'll apply that. And then the other one we're going to want to turn on here is, I believe, under language. Yep, right there. OpenMP support. So we want OpenMP. So let's just make sure we do this for all of our different configurations, just so that we don't miss it. Yes, OpenMP and multiprocessor. There we go. Turn on multiprocessor. And then we'll turn on language, OpenMP. There we go. There's also under like debugging, and it's one of these C-related ones. It will talk about a multi-thread DLL. It should automatically set that up based on a setting, the other settings. But in case you might need to switch this from multi-threaded to multi-thread debug and stuff like that. Just a heads up on that particular one. But it should handle it for you. I'm going to click OK. So we've set this up. Okay. So I've talked about how great OpenMP is, right? And I've hyped it up in sort of this intro here, as much as you can hype up writing software. I'm going to go sort of down this rabbit hole, and we're going to go from there. So the first thing that we want to do is, let's say we want to write an algorithm to do something. So in this case, I'm going to put a for loop. 0 I is less than, we'll say, 10,000. Right? And maybe our logic here has to do something particularly intensive. I don't know, we can iterate, or we can not iterate over, but we can do several different things on an array. So let's say we have our big data array here, and basically we'll want to do some sort of math on it. We'll start off here by just writing a value to data of I equals 0. We'll make it super simple, right? But we'll make this much more complicated. Now, if we go to run this code, and then I'll print right. Printf. There we go. So if I go to actually build and run this, it's not going to be the world's most exciting application here, but it takes a little bit of time to run. And there we go. We printed out, 10,000 zeros essentially. Cool. Okay. Took quite a bit of time to run. I promise you that if I remove this printf here and I run it, it'll execute super quickly like that. But the printf slows it down, so that's fine. So we just, added a whole bunch of things to this. And if we look at my computer here, I have my process manager. We'll refer to this a bit as it runs. You'll see that nothing really going on there. It's kind of boring. So there we go. Pretty simple single-threaded application. And if I make this bigger, if I add another 0, we're just going to be sitting here longer while it does that, right? But we'll leave it at 10,000 to start. Now let's assume that we need to do some math on this, or something a little bit more complicated. So why don't we make a const int scale equals 254. It's coming up with a number there, and I'll say, I'll do another for loop. There we go. And we'll say if I modulo 7, and well, maybe I modulo 3 equals 0. So this basically says every third element. We're going to do data equals scale times I divided by, or times I plus 796. I don't know, that's probably going to overflow. Just guessing, because scale is going to be 254, potentially times a really big number, but we'll see, and we'll let this run. And if we go and we watch we first have to fill in all of the zeros, which is great. And then there we go. We have a whole bunch of zeros still in that. And then we have some really big numbers. That's cool. We're just building out a little application here, with some logic. Maybe we'll say if I modulo 2 equals 1, so this is going to be basically every odd number. We'll say data of I plus equals 17, and then data of I times equals 2, or data of, times equals 2. So if we run this again, we're just getting a little more complicated. A whole bunch of zeros have to fill in first. And it starts all over, and it starts filling in some values. See a whole bunch of 34s in there. Cool. So we're building up a little bit of an application, and it's doing sort of fun stuff, and then we'll say maybe there's an else statement here just to make it even more interesting, right? And we'll do plus, how about we do minus equals 27, and then times it by 4. Sure. This will be a fun and interesting, number, and we can go up here and we can see that, lots of stuff happened, and cool. Okay, can we make this run faster? Because this is doing a whole bunch of stuff largely independently. Can we make this run any more efficiently? And the answer is yes. And if we go to our cheat sheet here, we can use some of these variables to sort of learn about OpenMP. So the first one we're going to take a look at here is going to be this pragma OpenMP 4. And this is for our for loops. So I'm going to go ahead and put down on here pragma OMP 4. And then, or I can just put down pragma OpenMP 4. And it will go and it will run my for loops here. So sorry, looking here at a OpenMP parallel 4. So this is basically going to parallelize this for loop, and then we can then say, if I want something to be private, in this case I want I to be private, private means it isn't shared across everything. So basically we're just adding this pragma, and if I go to run it now, we'll see it does all the zeros first, And then it goes much quicker, and you'll notice that it prints things out of order. And that's because the parallel 4 actually divides the workload among all of my various processing nodes. And, you know, if we really want to make this take a long time, I'll add another 4 int j equals 0, j is less than say 1,000 times I, make it a really big number, right? J plus plus, and then we'll just say if j modulo 2 equals 0, do something else, do something else. And we'll say this is going to be data of I plus plus, data of I minus equals 2. There we go. So I'll make something either incrementally larger. Actually, we'll just make them incrementally smaller. There we go. So this is really going to take a long time, conceivably. If we go to run this, oh, I got some build errors. Oh, semicolon there. Go ahead and run this. It's really going to take a long time if I do it serially. But if I run this parallel, it should go pretty quick. So here's what I'll do to sort of show this off. So we'll first run this serially. And let's see how long this thing takes to run. Should take a good long while. It's going much slower, as you can tell, than we were last time. And if we look at my process monitor, we see that we're definitely peaking one CPU core here. Again, this is the non-parallelized example. I commented out that pragma. We're still going. We're halfway there. It's just going to get longer. It gets exponentially bigger as we go forward, right? So it's really cooking. And this computer here has, as you can see, quite a number of cores, and it runs quite quickly. But we're really sort of pegging things out. And if we're watching our timer up here, we're well over a minute into this. We haven't used too much memory, but we're a minute into this overall process. 1 minute, 17, 18 seconds. It's still going. Minute 30. We're almost done. We're at 9,500. We need to get to 10,000, or 999, or 9,999. So we're very close. And there we go. We're done. And we ran there, as you can see, for the better part of a minute, 2 minutes there. Now I'm going to turn on this Pragma Parallel 4, OpenMP 4, and it's going to make this I be private. I'm going to run the same thing again. I'm going to pop up the CPU monitor and take a look at what happens now among all the CPUs on the computer. They're all being used at 100%. If I pull up the actual application itself, it's hard to sort of keep track on where it's going, because what the OpenMP Pragma has done is it's told the compiler, decompose this problem and spread it among all my available processors. So you see, we're done there in 20 seconds. And you can see a very big spike among all the different processors, not just one. So it's one of the advantages of OpenMP. You might be like, I don't truly believe that you're running all these different threads, on different processors. So what we can do, I'm going to go over here and pull this back over here, is we're actually going to look up and print those thread IDs as well. So one of the cool things that you can do in OpenMP is you can find out your threads. So you can get OpenMP Where is it here? OpenMP get thread num. So this function, as you can read it here, will basically tell you what your thread number is in this process. So I'm going to add that to this. It's OMP underscore get underscore thread underscore num. And we'll call this ID. Computed on thread %d. There we go. I'll just add that to my printf statement. So if I go and I recompile and rerun this, we watch it run. So it's really hogging all the CPU, right? It's taking it, it's split it up and sort of sharing it. See, it's sort of stepping down in terms of utilization, which means that we're probably doing all sorts of stuff. But you can see all the different threads there printing. And we had, you know, thread 0 to thread 11 running, and you can sort of see them all counting up in how they print out. You know, there's thread 239, you know. You can see everything print out, which is kind of cool. So this is sort of the basics of OpenMP. Now what's really cool is that this program still runs if I comment this out and I run it. You know, we saw it before. I even added in that, you know, get thread number. It still builds. OpenMP just sort of is there, and you can see they're all running on thread 0. And they're going to spend a good long while just running on thread 0. But that's sort of the advantage of this approach to parallel computing, is that you don't have to have, you know, any sort of major you know, background in parallel computing to make it happen. If you have the correct sort of application structure, you can take advantage of it. And sometimes you can take advantage of it even if you don't. I mean, these are obviously the easy cases, so I can also do the same thing, you know, up here for setting all this memory, spread it out over the processors. You know, if I really want to, it might be more interesting to say, you know, spread that and set it to thread IDs, just to have a different, you know, set of numbers initially. If we watch that, you know, we'll have a very big set of numbers that are different going through here. But you can do stuff like that. But you don't have to use it within the concept of a for loop, though. Maybe I just want to run a few threads in parallel to do some basic comparison. So what I'm going to do here is I'm going to put in another OMP, Pragma OpenMP, sorry. So I have another Pragma OpenMP parallel. Put down some brackets here just to group it. You know, brackets are a logical grouping thing in C. So I have my now grouping. I can put a whole bunch of content in here. So if I want to get my thread number, that's great. Cool. And then maybe I want to just print it. You know. That's cool. And I will comment this out. There's a lovely button up here that I can just comment the entire block out. It makes life a little bit easier. Now if I go and I run this, it runs, get all the different threads going, and then it kept all those threads running. Cool. Now I'm going to let you in on a little secret. This computer actually doesn't have 12 true cores. It has 12 logical cores, and 6 of them are true. So maybe if I was doing something a little bit more complex, like using floating point values, I might want to spread this out a bit and only use 6 threads. Well, if we go to our OpenMP reference, it actually gives us a little bit of help for that. So you can actually set up a max number of threads as well. So where's it? OpenMP set threads sets the number of threads used for you know, subsequent parallel regions. So if I want to do that, let's say I only want to set this OMP underscore set num threads. There we go. And let's say I only want to have 2. Sounds fine to me. I picked a number. It only did 2. So I can actually set the number of threads. I can also set this to be a bigger number. So I could say 100. Right? Seems logical. Can set it to a bigger number. And it creates 100 threads. Now, if we want to leave this application the way that we had it, and we'll just remove this commented out block, and we'll go back to things. So now we're going to run 100 threads when we get to that big section, right? You can see some of those numbers peeking up there on the screen. You can see this thing's running. It should run faster, right? I added more threads, more compute power, go faster. Maybe. It depends on the complexity of the problem and how it breaks things up. So in this particular case, it ran in about the same amount of time, but looks like it used the processors a little bit more completely because there was always a thread blocked ready to go versus looping over something. But that's not always the case. You can also scale it way down. If we want to say only use 4 and run it. Let me see our application running, and I'll pop back up the process manager here. You'll see that only a few processors are running, sort of more full bore. I see 2, 3, and there's a 4th one. Which one is the 4th one? I guess I'm only seeing 3. So the other thing is this is a thread level parallelism, so it can be assigned to processors, or it might take a break or whatever. It sort of relies on the operating system to schedule. There we go. We're done. So we can see that really didn't finish all that much faster, all that much better. If I say put 500 threads in here, we would expect this thing to go gangbusters and be super duper quick. Consume all the available computing resources. And you can look at that thing go. We said about 2 minutes was the non-sped up time, and that took it down to about 20 seconds. And just sort of spread things out. So you can even do this, like I said, for non-for loops. You can do this, if you need to set a certain number of threads and you want to compute something, you can do that here. I'm going to set this to 2 just for some of this next logic here, just to make it simple. Sometimes, well, I guess I'll flip over the side-by-side because it's probably going to be a bit more of explanation. When you do threading on a computer, there's sort of 2 classical ways to do it, right? One is OpenMP that we've been looking at here, and it's super simple. I didn't have to worry about memory. I didn't have to worry about anything like that. It actually keeps all my memory coherent and partitions it and makes a copy of things where appropriate and negotiates all that for me, which is a huge, huge savings. And that's why I can scale this up pretty quickly, is because my memory is all relatively independent. If you had interdependencies between things, you have semaphores and stuff being locked under the hood. The other way you can do this is you can do this all manually using threads. You can use pthreads or whatever, depending on your operating system. You can use Windows threads or whatever. And when you create these threads, you're basically saying, create a new thread, and I'm going to set up the memory, and I'm going to handle all that synchronization between things. And that can be a pain, especially if you're a novice programmer. That can be a real pain to set up, locking a mutex and signaling on a condition variable so that you sort of have your semaphores locking critical sections of your code so that you're not overwriting data and using atomic variables and all that stuff. And I'm sure most of what I just said doesn't make sense to anyone watching, or might make sense to some folks, but that's a very, very complicated process for you to understand and keep track of, and it can lead to a lot of errors in your development. In OpenMP here, you can just plop down a parallel section, and you can sort of do something that achieves the same goal is having two completely independent threads that share information. And I'll show you how to do that right now. This is not like the best programming form per se, but it's using a tool to complete a job quickly. And I actually use this approach quite a bit when I'm just trying to get something quick and dirty put together, and maybe I only need 2 or 3 threads, and the logic is relatively simple. So let me go back over here to my computer. So I'll get my thread ID. I'll print that just for sake. And then I'll say if, ID equals 0, because I know that's going to be the first one that's going to happen, do something else, do something else. So maybe this is going to be print doing lots of computation. And then this one will be waiting for user input. Cool. And I can run this and have these 2 threads do something completely different. And you'll see here at the very end of that long initial loop, you'll see that each one sort of printed independently, and we didn't see that same message printed twice. And I'll put a /n between them. Right? So maybe in this case, I have an integer here. I'll throw another int up here and call this display data and input data. Right? So maybe we say here, put a, basically say maybe our computation is waiting for while, input data equals 0. Wait, I could, do whatever to wait there, and then say display data equals input data plus 3. There we go. And then if I want to put in a wait, I'm going to cheat here because this should be simple. Windows.h. I should just be able to do a sleep. There we go. Windows.h includes a boatload of things. So I know it includes the timing and threading stuff. So that's why I was just like, I'm just going to cheat and throw that in there. Ideally, you wouldn't want to include something so big unless you absolutely have to. You would try and just include the required header files. But, here this is sleep in milliseconds. So I'll sleep, 100. Or I'll sleep, 5. That's fine. Doesn't need to wait a lot. And then display data, and then that'll be done. And then in this particular one, I'll say while, display data 0. That should be a capital S there. And I'll start off by saying, sleep 25, and then input data equals 10. Sure, there we go. Now, to do this properly, I'm going to want to declare some values shared. So shared is another keyword that you can use. In this case, I want it to be display data, and then input data. You don't have to include shared. OpenMP will assume everything is shared unless you say otherwise. But that is the proper way to be explicit. If you followed along in the series, you'll know I like to be explicit on everything. So that is how you would be explicit in terms of setting up your values. So if we go and we run this, so there we go, doing lots of computation, waiting for input. There we go. So pretty quick. If I want to go down here, put waiting for input out front, and I will make it sleep for 2.5 seconds just so we can see it. And then it should return pretty much immediately for what we're doing. So here we go. Waiting for user input. There we go. And it pretty much returned immediately. So that's an easy way that we can exchange data between threads and sort of set that up. And, you know, doing it with if statements, it's kind of gross to look at on a screen. If you break everything up into functions, that kind of helps. You could do switch statements in there too based on ID. But it does get kind of gross as it gets more and more complex. But if you're doing something quick and dirty, OpenMP is my go-to for this sort of, you know, quick way to make a parallel application, just because it removes so many barriers for me. And that's sort of the intention behind it, is to be very quick and easy. Speaking of barriers, that leads me to a nice little segue here. I'm going to see if I can uncomment all of this. There we go. There's actually another command, I'll bring back up the cheat sheet here, that we need to be familiar with. And it's the concept of a barrier. So where are we looking at? Let's see if they have it on here. Target update. I'm curious. There we go, barrier. So barrier, Pragma OpenMP barrier. Like I said, this is a great cheat sheet. So we're actually going to use a Pragma OpenMP barrier. And what a Pragma OpenMP barrier does is it says everything needs to get to this, all the threads need to get to this point before we can move on. So that's kind of helpful if you're trying to do something that's thread synchronized. So for instance, in this particular case, you know, let's say I wanted to put a Pragma open, there we go. Put a barrier there. Why might we want to put a barrier and get all the threads to complete this before we move on as we break it up? Maybe we need to use half of this data and have it sort of pre-computed, you know, and synchronize, get all of that computation done, and then we can do this second part. So what will actually happen is threads will all get here, and then they will wait each time they run that loop until all threads hit that barrier, which is kind of handy, especially if you max your exact number of threads to the number of, you know, like loops that you have. So in this particular case, let's say I wanted to say data of I plus 1. We'll say this is if I, or yeah, I is less than otherwise, we will say data I sub 0. Basically what we're doing here is we're saying take the next value, and then we're rolling over here on the bottom, you know, based on our number. So we need to know, you know, what all these data values are before we go and do this math. So let's say I come up here, I'm going to comment out this parallel section. So there's my comment section, and I'm going to set my number of threads to be 10,000. We'll make it really big. Lots of threads, so that each of them sort of execute in order. And they're all going to run now. Oh, that's right. You can't use an OpenMP barrier inside of a for statement. We'll undo all that, and we'll go back to... I forgot about that. There we go. We'll go back to this logic here, and we'll say, you know, maybe I'll put my Pragma barrier here, so we have to at least complete all this. I'll make this pretty simple. So I will say we have 100 threads, just to be ornery, and data of ID equals 250, right? And then our barrier is going to happen, and then we'll say data if ID equals 250 or 249, data of 0 plus plus, else data of ID minus minus. Oh. There we go. So what's going to happen now is this is all going to run, and it should be pretty quick. Oh, I forgot to comment out the bottom section. My bad. Should finish pretty quickly. We have 100 threads going. There we go. So yeah, so we want to run this, and it should go pretty quickly. There we go. Didn't have anything to print here. Maybe I want to print all these values. Well, I'll put a for loop in here. That'll be great, right? Int j is less than, I think there's what, 10,000 variables? Sure. Less than 10,000. Int j equals 0. J is less than 10,000. By the way, I have a new appreciation for every one of my professors that has programmed live in front of me, because it is actually quite difficult. And you mess up a lot and you make a lot of stupid mistakes. So shout out to all of them. At %d is %d j and sorry. Yeah. Data of j. There we go. That's a nice little quick way to print things out, right? It's just that for loop. It's the same sort of thing we did up here. Should be quick and easy, right? Whoa, that's a lot of printing. And that's not just a lot of printing because I didn't put in the /n's on the end. That's a lot of printing. What's going on here? Well, we hit this barrier. That's good news. I'm going to stop that. Put the /n on the back. But we probably need another barrier. We probably want all the threads to finish their computation before they go on to printing that. That'll definitely make the data correct, because I can guarantee that we had some data being incorrect. But we have another problem here. Is maybe we only need one thread to execute this. We could move it outside of the parallel section. That's doable. But what if we wanted to also print, the starting values up here? Well, how can we do that? Well, again, I'm going to pull up the cheat sheet because I can't stress this enough on how great this cheat sheet is. There's another parallel section that we can use, a special type. So there's a single section. I'm trying to see if it finds it for me. So there we go. Single. It's only executed by one of the threads in the team. So that's a nifty little way to do it. And there's actually another command on here that's called no-wait. And you'll see what no-wait, there's probably a bunch of them. I don't know if it has a lovely header. It probably does because it's a great document. But anyway, the idea is that whenever you have a OpenMP section like this, we probably want a barrier before this one, right? Is that there's an implicit OpenMP barrier added. If I put in OpenMP Single, for example, and I like to be explicit, like I said, put that on there, it's going to execute this just on one thread. So we don't have all of our threads doing this particular loop. And that way, I don't need the barrier there, so to speak. So that's kind of handy, right? The no wait would just force it to immediately go. It wouldn't wait for all the threads to catch up to that particular point. So if I go and I run this, I'm going to put breakpoint actually right here. There we go. You'll see that it has updated every value. There we go. And printed them before it, and it only printed them once. We don't have them printed like 5 times. So there we go. And now each thread is going to hit it. By the way, debugging in OpenMP or really any parallel computing becomes a lot more painful because each thread will hit your breakpoints. But yeah, so there we go. So that does our OpenMP Single, which removes the need for another barrier. So I can run this. There we go. That actually went a little bit quicker than I expected. I'm curious as to why. Let's find out. When I run this, so we hit that particular one. Oh, it did actually probably run them both. Just in printing them out, they're all the same, so we can't tell. So maybe this last one only prints up to 100, just so that we can tell. If I go and I run this again, so there we go. It set all those first ones' values to 0. Or at least printed them all. So there we go. There's all of our data, 259. There's 249. There we go. Not bad. That probably, doesn't matter because we're doing less of them, but if ID equals 99. There we go. So there we go. We subtracted all those out, and then I bet you this first one here. So if we look at this, it looks like we're not using all 100 threads. If you see this here, we're sort of stopping after 64 threads. So there must be a maximum number of threads set on my computer. Cool. I wonder if OpenMP has a solution for that. And this was actually carefully orchestrated to sort of hit all of these. There is actually, you can get the max number of threads, required for the computer. So there we go. Get max threads. Oh, that's strange. It seemed like it had a little bit of a brain fart there. Let's try it again. There we go. We hit that breakpoint, and it says we have a max thread count of 12. So there we go. We know that we can only have 12 threads. Now, why is it saying that we can only have 12 threads? Well, that's because that's all the number of logical processors that I have on my computer. So even when I set the thread count higher, like I just did, the max thread count that it hits is only going to be 64. This again comes down to some OpenMP settings, and it's not really something that you get to change. You can get the max number of threads, but you don't really have the ability to set them. So you're sort of stuck in that particular limit. So so you can get the max thread limit. We'll get OpenMP thread limit. What is the exact command there? Get thread limit. Is it OpenMP get thread limit? I should probably just copy it. OMP get thread limit. Yeah. So evidently, I don't have the limit that it will let me get on this particular. It might not be the latest version of OpenMP on the computer here, which is more than likely my fault. But there is definitely an implicit upper bounds to the number of threads that you can get, and it relates largely to the number of processors that you can have on your computer. So that's just sort of one aspect of OpenMP threading. So there are sort of these upper bounds. So if I set this even to, say, 5,000, and I actually just nope. I'll set that back to 5,000, and I go to run this, and it's off doing its thing counting. We still only have a maximum of 64 threads. And that's consistent with what we saw before we were printing this, of only the first 64 values down here getting set. So that's just a interesting, sort of limit that OpenMP is imposing on the system. So I guess this would be ID 63, just to have it roll over. If we go and it's running again, if we scroll up, we'll see that we have 249, 249, 249, and then the value of 263. So if ID equals 63, it increments it, increments the value of 0. So there you go. Another little bit of, and that's different to every computer. Depends on your computer's resources. Now there are some other aspects to this cheat sheet. I haven't just been referring to this because I want to go in great detail on it. And this is sort of an overview thread, and I got all of 5 minutes left, and we can go on this for days and days and days. But I did want to highlight a few things as you start playing with it, because first of all, this is something amazing to play with, and I highly recommend it. That you just start up C# or sorry C++ in Visual Studio and start playing with it. But as this has sort of grown towards more scalable computing, it has some new concepts in here that you might find really helpful. For instance, this concept of a SIMD, single instruction multiple data. This is if you want to operate on large data sets and you need to apply the same thing for it. So like a really great example of SIMD that actually sort of I used in some of my PhD research is applying weight matrices. So you have lots of data that you need to apply specific values to, and doing some of that. Single instruction, multiple data. So that's exactly what that does. And it uses a special part of your processor that will actually let you take advantage of that. So that's a great one right there to take advantage of. But even cooler than that is that the latest versions of OpenMP have added this concept of a target. And a target is basically a device that you want to execute on. So you can target like a GPU and that sort of thing. So that is another great tool. I have an NVIDIA GTX 1080 Ti in my computer, so I could add that, for example, as a target. And if you're interested in GPU computing, let me know in the comments or send me a message, because I can totally do a whole thing just on CUDA, on OpenMP, on OpenCL, on a whole bunch of different programming abilities for GPUs. That's a big part of my doctoral research. You can also do distributed computing through OpenMP now, which is really cool. Originally, OpenMP was sort of stuck in this sort of multi-threaded concept. And if you needed to exchange messages, which is how you would do a larger setup, you would either need to do it through a network packet, or you'd use something like OpenMPI, which is extremely difficult to keep straight when you're in a conversation and you're mentioning both of them. So if you want to go to a larger system now, though, the latest OpenMP, the 4.0 API, as you can see over here, and I'll switch it so you can sort of see it better, it now also offers the ability for distributed parallelism. So those are really big sort of wins added to this. There are a boatload of keyword and functions that you can do inside OpenMP, and like I said, this hour was just supposed to be a high-level, quick, get you up and running. I could probably do a whole nother day or two just on OpenMP on this, but I wanted to make sure that everyone saw that there is documentation out there, and you can totally check it out, and find out information, do all that sort of stuff to get comfortable with this. Parallel computing is something that is almost a necessity now to take full advantage of a computer. As you've seen, many of these applications that we've done to date have been single-threaded, and maybe you want to have your networking like we did yesterday on one thread, and your logic on another thread, and you want to spread things out, or you're dealing with that sort of stuff. So this is a big part of sort of making those applications truly take advantage of the hardware, and in this case, just my examples here, just the CPU hardware, but ultimately, even the GPU hardware to make good use of a computer, so that in this case, all 12 of my logical cores are not sitting there idle, and right now, like it's clocking in at 3.67 gigahertz on 12 threads all running at the same time, and that's a great use of the compute resources rather than just running one thread at full bore for a long time. So that more or less concludes where I wanted to get through on the parallel computing side. I am going to comment this through the roof for everyone, and I'll leave the video running for that. I'm also going to push this up to GitHub so you can totally check it out. Like I said, super simple introduction to some parallel computing concepts here, and something that you might want to play with some more on your own. I recommend trying it. The worst thing you're going to do is cause a blue screen death on your computer and have to restart. It's there's no real sort of long-term damage doing this, and you couple a big processor with a lot of memory. I'm sure you've probably seen here that my computer here is rocking 64 gigs of memory. I can do large computing jobs even on my home computer here. And take advantage of all the hardware resources, having multiple threads, accessing all that memory, and a GPU to accelerate stuff. And your average desktop computer also has a lot of those resources as well. You don't need to have a sort of gaming rig like what I have to, be able to take advantage of that. So I recommend getting into this more as you start to write more applications. And this will make you a better developer, and definitely teach you a lot about what is very much, I'd say, the future, but the future is now in sort of parallel computing. So Anyway, if you have any comments or questions, you can leave them in the chat or leave them in the comments section below, or you can send me a message on my blog. This concludes what I set up for software sessions. I might come back and do one here or there. I haven't seen anyone be like, yes, continue them daily next week, and I haven't seen anyone say no. So we'll see sort of how that goes. If you feel strongly either way, feel free to let me know as well. If there's specific topics you want me to dig into, if you want me to spend an entire hour just talking on, OpenMP, single sections and how you can use those, I'm happy to do that as well. So I want to thank everyone for joining me for this. And hopefully you learned something and you got some benefit out of it. So thanks everyone, and I'll catch you later. There we go. Everything's pushed. So this is Andy. Thanks for watching and signing off.